Hello everyone, welcome to my channel Tricks for Maths. In my channel you are getting videos on Vedic mathematical tricks and techniques to solve various type of mathematical problems. Parallelly you are getting videos on grade 10 mathematics of CBSE syllabus. We have started real numbers. I hope you have seen other videos on real numbers. If not, please subscribe my channel, go to my channel and please get the videos on real numbers. So far, we have covered Euclid's division algorithm as well as revisiting irrational numbers and revisiting rational numbers and their decimal expansion. You will get separate videos on these three topics. Today we are learning the Fundamental Theorem of Arithmetic. So what do you mean by Fundamental Theorem of Arithmetic? In order to learn that, before going to the particular theorem, we need to understand a few things which related to Fundamental Theorem of Arithmetic. That is prime factorization of a number. What is prime factorization of a number? Yes, we have already learned that. We have solved so many problems. Prime factorization is nothing but it's a method to find the prime factors of a given number. Say it's a composite number only, right? So we know that there are two types of numbers. One is prime number, which is having the factor 1 and the number itself. It's called prime numbers. And the number which is having factors 1 and the number itself and other numbers also. That is called composite number, right? So now let us go for a few examples to understand better what is prime factorization. Then we will move to Fundamental Theorem of Arithmetic, which is based on prime factorization. Let me take any example. I will take here 12. So how will you do the prime factorization for this composite number? Yes, you will express it a product of prime factors, right? So how will you write? We know I can write it as 2 6, right? 2 multiplied by 6. But 6 is not a prime number. I am expressing this 12 into its products of prime numbers only. So again 6 can be written as, so I'll write 2 as it is. 6 can be written as 2 into 3. Yes, this 6 can be represented as 2 into 3. So all the three numbers here are prime numbers. I can't go further, right? Because 2 and 3 are prime numbers. So what I did here, I expressed this 12 as product of prime numbers, right? This is called prime factorization. So here I can go for one more step. How many times 2 is repeated here? Yes, 2 times. So I can represent this as in the exponential form. So 2 raised to 2 multiplied by 3. Here the exponent is 1. You know, right? So 2 raised to 2 multiplied by 3 is the prime factorization for 12 here. Let me take one more example. I'll take 18 here. Okay, so how will you express this? 2 into 9. Okay, again I will write 2 into 3 into 3. Okay, 9 can be written as 3 into 3. So the prime factorization for 18 is 2 raised to 1 multiplied by 3 raised to, need not to write 1 here. 2 multiplied by 3 square is the prime factorization for 18. So in both the cases you have observed that any composite number can be expressed in the form of product of its prime factors, that too in exponential form, right? So this is nothing but Fundamental Theorem of Arithmetic. I hope you have understood the concept. So what does it say? Every composite number can be expressed or factorized. Okay, we factorized. Okay, every composite number can be expressed as a product of primes. Okay, we need to express it in a form of prime products only, and this factorization is unique. Okay, this factorization is unique apart from the order in which the prime factor occurs. So you have understood till this, right? It can be expressed in the form of product of prime numbers. Okay, till this you have understood. You're observing one more term here, unique. What does it mean? Okay, yes, we have taken 12 and we express it as 2 square multiplied by 3. Am I correct? And we have taken 18 also and I expressed it as 3 square. Okay, 2 multiplied by 3 square. So, you are observing in each the cases 2 into 2 into 3. Okay, only one type of prime factorization you got. You can't express this 12 in any other way, like 2 into 3 into 5. You will not get 12. Okay, any other prime factors you can't take. So it is nothing but unique. Okay, so if you express a composite number into its product of prime numbers, you will get only one set. Okay, so in the case of 18 also, the prime factorization is only in one way, that is 2 into 3 square. Okay, and you are observing one more word here, order, apart from the order in which the prime factor occurs. That means here I have written 2 into 2 into 3. Okay, this is nothing but 3 into 2 into 2. Okay, or you can write 2 into 3 into 2. But what you have done, you have taken 2 two times and 3 only one time. So it is a unique and the order may be different, right? However you write these 2, 2 and 3, it will be the prime factorization of 12 here. Okay, in the case of 18 also 2 and 3 square will come. Okay, not other any prime numbers. Okay, so how you can write 3 square into 2 or 3 into 2 into 3. Okay, order may be different but it will be unique. So this is nothing but fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factor occurs. Okay, we will solve by taking a larger number, then you will come to know how you are taking prime numbers to factorize that and how the order will be and how will you use that prime factorization for further calculation. To take the example, I am switching my content to your exercise 1.2 itself. That means I am taking examples from your exercise so that we can solve your exercise problems, right? So first question is, express each number as a product of its prime factors. We just understood what is prime factorization. So we will take any two examples. I will take 156 and 3825. We will express it product of its prime factors. So let me take 156 first. So how you are going to prime factorization? It is ending with 6. So I can go for 2 here. It is divisible by 2, right? So 2 7s is 14. So 1 is carryover 16. So 2 8s is 16. Yes. Again it is ending with 8. So I will go for 2 only. 2 3s are 6 and 2 9s are 18. Now it is not ending with 0, 2, 4, 6 or 8. It is ending with 9. I will check for 3. The next prime number. Okay. 3 1s are 3 3s are. Now I can't go for 3 or 7 or 11, right? It is 13. 13 is a prime number. 13 1s are 13. You know the process, right? So now I can express this 156 as 2. These prime numbers I am taking 2 multiplied by 2 multiplied by 3 multiplied by 13. This is the unique way. Okay, so how can I write one more step? 2 is repeated 2 times. So 2 square multiplied by 3 multiplied by 13 is the prime factorization for 156. We have expressed this in exponential form also. Right? I hope you have understood. Let us go for one more question, that is 3825. So it is ending with 5. Yes, I can directly go for 5 here. So 5 7s is 35, 3 is remaining 32, 5 6s are 30, 25, 5 5s are 25. Again it is ending with 5. I will go for 5 itself. 5 1s are 5, 26, 5 5s are 25, 15, 5 3s are. Okay, now I will go for, it is 5 plus 1 is 6 plus 3, so 9. So it is divisible by 3, correct? So 3 5s are 15 and 1s are here. Again 5 plus 1 is 6, it is divisible by 3. So I will take 3 once again. 3 1s are 3, 21, 3 7s are 17 is nothing but a prime number. So I will go for 17. 17 ones are 17. So these many prime numbers I got here. So 3825 can be written as 5 multiplied by 5 multiplied by 3 multiplied by 3 multiplied by 7. Or in other words, 5 is repeated 2 times and 3 is repeated 2 times and 17. Here you can observe that in the Fundamental Theorem of Arithmetic, we come up with two different words. Unique and order may be different. See, first I have started with 5, okay, and then I taken 3, okay. So it can be written as 5 into 5, 3 into 3 and so on. If you divide the whole number initially by 3 itself, you will get 3 first. That means order is changed, right? Okay, but you will get the unique value, okay. So 3 into 3, that means 3 square or 5 square, 17 you can write, or 17, 5 square, 3 square you can write with the multiplication sign. Okay, I hope you have understood the fundamental arithmetic theorem. Okay, so we now understood how to represent a number in its prime factorization form. We have solved your exercise problem also. That means representing any composite number into its product of prime factors. Yes. So why you will use this prime factorization method for further calculation in finding HCF and LCM of pair of numbers, right? So let us go for one example here. Find the HCF and LCM of the following pair of integers. Okay, here I have taken 26 and 91. Let us solve using prime factorization. Okay, that is nothing but Fundamental Theorem of Arithmetic. So 26 and 91 separately we need to find out. So first I will go for 26. It is ending with 6. So I'll start with 2. 2 1s are, 2 3s are, 13 is a prime number. So I can directly go for 13. So 26 can be written as 2 into 13. Okay. Yes. Now 91. So which number can divide 91 exactly? Ending with 1, we can't go for 2, and it is 9 plus 1 gives you 10, so it's not divisible 3. And now 7, okay, I can check for 7, 7 ones are 21, yes, 7 ones are 7, so 2 is carryover, 2 1 21, 7 3s is 21, okay, again 13 ones are 13. So 91 can be written as 7 into 13, okay, 7 into 13. Now you have done the prime factorization for both the numbers. So how will you find out HCF and LCM? Yes, we have learned that, right? HCF is nothing but which prime number is repeated least number of time. Okay, you need to compare in both the numbers. See, it is 13 here, it is repeated, okay, it is common for both the numbers, and the least exponent, okay, it is 1. 13 is here, 13 is here. In this example, no worries. So 30 raised to 1, 13 raised to 1 is here. So you can directly take 13. Okay, 13 is common for both the numbers. So 13 is the HCF. I will write here HCF is 13. Okay. Now LCM. How will you find LCM? Yes, we know that we will write the common only one time. This 13 is a common here. So we will write 13. And then the other values, okay, 2 and 7 also, we will take the product of that. So LCM is here, LCM is equal to 13 multiplied by 2 multiplied by 7. So answer is the LCM, okay, 7 2s is 14, 13 into 14, you are going to write the answer. Here answer is 182, okay. So LCM is 182 and HCF is 13 for the given pair of integer. Okay, let us move to the second problem. 510 and 92 I have taken here. So let us go for 510 first. It is ending with 0. I can go for 2, or 5 and 10 I am observing, I can directly go for 5 also. I will just take 5 only. 5 ones are and 0, 5 twos are 10. Okay. Now again 2 fives are 10. Okay, 2 ones are. Now 5 plus 1 is 6. So I can go for here 3. Okay, 3 ones are 21. 3 sevens are is 21. 17 ones are. Okay. So 510 can be written as 5 multiplied by 2 multiplied by 3 multiplied by 7. Any prime number you can take and divide, but go for exact division. Okay, check for that. So second number is 92 here. I'll go for prime factorization, which start with 2. 2 fours are 8, 12, 2 6 are. Again 2 twos are, 2 threes are. Okay, 23 is a prime number. Okay, it can't be divisible by any other number, so 23 ones are 23. So 92 can be written as 2 into 23. Okay, now for HCF you need to find out the common prime number, and that too the exponent should be least. Okay, so here 2 is only common, but here it is 2 1. I will rewrite this 92. This is 2 square multiplied by 23. Okay, so in order to find the HCF, 2 is common for both the numbers 510 and 92, and here 2 and 2 square is there. We need to take 2 only. Okay, least exponent number. Okay, so HCF is 2 here. So what about LCM then? Okay, LCM can be written as 2 is common, but the greater exponent we will take, right? 2 square, I will write 2 into 2 itself, and if I take 2 into 2, okay, the remaining 5 3 17 23. Okay, multiplied by 5 multiplied by 3 multiplied by 17 multiplied by 23. If you go for multiplication, you will get the product. That product will be the LCM of the given pair. So the answer is 23,460 is the answer. Please go for multiplication. You will get the correct answer. Please cross check it. So HCF is 2 and the LCM is 23,460. We have taken different examples. See, in these two examples, we got HCF 13 and LCM is 182 for 26 and 91. In the second example, I got 2 as HCF and 23,460 as my LCM. Can we get any relation between the numbers and HCF and LCM? Can we go for multiplication by taking HCF and LCM at a time and the product of these two numbers? Let me check for the first example, this one 26 and 91. So 26 multiplied by 91. I will just find out the answer and I will write. Again this HCF multiplied by LCM, that is 13 multiplied by 182. So what will be our answer? If you go for product of 26 and 91, you will get 2366 as your answer. Similarly, if you go for the product of this 13 and 182 also, you will get the same answer, 2366. So what are you observing here? Yes, the product of these two numbers, what they have given, okay, and what LCM and HCF, what we found for the same number, the product of those two is also equal to the product of the given number. Okay, so let us go for the second example also. 510, numbers are 510 and 92. We will get the product as well as product of this HCF and LCM. That is product of 2 and 23,460. So the product will be for 510 and 92 is 46,920. Okay, if you go for the product of these two also, HCF and LCM also, you will get 46,920 itself. So in the second example also, you are observing product of the numbers is equal to product of their HCF and LCM. So we can have relation between HCF and LCM for a given pair of numbers. So in general, what we can say, for any two positive integers A and B, HCF of AB multiplied by LCM of AB equals to the product of those numbers, okay, A and B. So we can take many examples, we can cross check this rule also. I have taken the numbers from your textbook itself, that means exercise 1.2. I have taken this 26 and 91, we covered this, and 592 also I covered. So please go for this third one and find out the answer. Okay, now for the third question, it is very simple. They have given three numbers. You can go for prime factorization for each and every number and you will represent it in a prime factorization method. Okay, so let us go for the fourth question. Given that HCF of 306 and 657 equals to 9 and find LCM of that pair. So how will you solve this question? Here they have given HCF. Okay, HCF is 9 and those two numbers also they have given. So what are the numbers here? 306 and 657. We know the rule, right? For given AB, the product of HCF and LCM is equal to product of those numbers. Here we have numbers also, A and B, and HCF also. Now it is very easy to find out the LCM, which is an unknown value, right? So by substituting the values in the place of HCF, I can substitute 9, okay, LCM as it is. So numbers are 306 and 657. So now in order to find this LCM, 9 goes here, okay, 9 divides product of those two numbers. So LCM is equal to 306 multiplied by 657 divided by 9. Okay, you can go for like this, 3 3s are 9. Okay, 3 1s are, 3 2s are, again 3 1s are, okay, 3 3s are 9 and 12 3 4s are. So 34 multiplied by 657 you can do. That gives you 22,338. That means LCM of 306 and 657 is 22,338. Let us move to next problem. Here they have given, check whether 6 raised to n can end with the digit 0 for any natural number n. It is based on Fundamental Theorem of Arithmetic itself. Okay, they are asking for this number 6 raised to n. That means here if you put any value for n, you will get different numbers. They are asking the number can end with 0 or not. Okay, so let us go for the solution. If any number will be ending with 0, then it should be divisible by 10. Do you agree? Yes, it is correct, because if it is the unit place value 0, then it is exactly divisible by 10. Okay, or in other words, it is also divisible by 2 and 5, because 10 can be written as 2 and 5. If it is divisible by 10, it can also be divisible by 2 and 5. Let me take 30. Okay, it is divisible by 10, right? Now I am going to check for 2 and 5 also. Yes, it can be divisible by 2 ending with 0, and it is divisible by 5. Yes, my condition is satisfied for this number. So we need to check whether 6 raised to n also can satisfy this condition. That means it is divisible by 10, or in other words, it is divisible by 2 and 5. So let us go for 6 raised to n now. Whether it can be expressed in the prime factorization like 2 and 5. Prime factors should be 2 and 5. Let us check that. So prime factorization of 6 raised to n is 2 3s, right? 6 is nothing but 2 3s, 2 raised to n or 3 raised to n we can write. So it is clear that we are not getting any 5, right? 5 in the prime factorization of 6 raised to n. But it should satisfy with the condition of 5 also, right? It should divisible by 5 also, but it's not satisfying that condition. So 6 raised to n will not be divisible by 5. That means it is not ending with 0. Okay. Therefore, 6 raised to n cannot end with the digit 0 for any natural number n. If you put any natural number in the place of n, the result will be not ending with 0. Yes. The next question in your exercise 1.2 is explain why 7 multiplied by 11 multiplied by 13 plus 13 and 7 multiplied by 6, 5, 4, 3, 2, 1 plus 5 are composite numbers. Okay, they are asking for this number and this number composite. They are telling that we need to prove that. Okay, so how will you prove? Let us go for first number. Okay, so in this question 7 multiplied by 11 multiplied by 13 plus 13, we can observe that, okay, 13 is common, right? You are observing two 13s here. So if I take common, we can write it as 13, 7 multiplied by 11 plus 1. I have taken 13, so 13 ones are 13. So I can write 13. So by solving this, 7 11s are, yes, it is 77 plus 1 is 78. Now 13 multiplied by 78. Okay, so here it is a one factor. Okay, it's a multiplication sign only, no? So 78 can be prime factorized, right? If you go for prime factorization for 78, it is 13 multiplied by 13 multiplied by 6. That means 78 can be written as 13 into 6 also, or you can go for prime factorization 6 also, 2 into 3. Okay, so what can be concluded? The given expression has 6 and 13 as its factors. Need not to go for prime factorization 6 also. A number is said to be a composite. It should have factors as other than 1 and the number itself, right? Here it is satisfying that condition. The given number, this first number is having factor 13 and 6. If I go for further prime factorization, you will get 2 and 3. So other than the number and 1, right? So it is a composite number. Yes. Let us go for the second example, that is here 7 multiplied by 6 and so on. For this number, okay, we can observe that they have given plus 5. These are all multiplied and this is plus 5. So if I take common 5, I will get 7, 6, 4, 3, 2, 1, all are multiplied plus 1. Okay, just go for calculation. You will get 1008 and this plus 1. Okay, plus 1. So that is nothing but 1009. But 1009 is cannot be further factorized. Okay, so we are observing that a number is having a number as a factor and 1. Yes, anyways it's a factor, and we are getting 5 and 1009 also as their factor, right? So it is a composite number. It is having the factors other than 1 and number itself, right? So it is a composite number. Yes, here it is the next problem, that is 7th one. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again? Okay, at the starting point. They have started at the same time, okay, at the same place, and they will go in the same direction. She takes 18 minutes and he takes 12 minutes. So when they will meet again, they are asking. Yes, we need to skip count of 18 and 12 and we need to get the same number after some time. What is that number? That means it is nothing but LCM, right? So for the 7th question, you need to find out LCM of, okay, LCM of 12 and 18. Okay, it's very easy. You can go for this. Just I will show here like this only. 2 6 are, okay, that is nothing but 2 into 3. Okay, so for 18 you can write 2 9s is nothing but 3 3s are. So for LCM, first write the common. Okay, here it is 2 and 3 are common. See, 2 is common and 3 is common. So I will write one time 2 and 3. Okay, again 2 and 3. that is nothing but 2 3s are 6, 6 6 are 36. So 36 is the LCM for this question. That means answer for the 7th question. We have solved all the problems of exercise 1.2 which is in your textbook, okay, with a concept explanation. I hope you have found this video very useful. Please use it. If you are new to my channel, please subscribe my channel to get all the videos on all the chapters as well as tricks in Vedic mathematics. Please share with your friends and do support. I will meet you with the next video. Till then, take care. Bye bye.